Okay, so in today's video, we're going to be doing some math for fun. We're given that the limit as x approaches infinity of 1 divided by the square root of x multiplied by the integral from 1 to x of the natural log of 1 plus 1 divided by square root t dt. So we're being asked to compute this question. We have a limit, an integral, and a natural log. So this is going to be interesting, and a square root function, so that's awesome. So one thing before I want to, before we get started, is I actually want to establish the fact first that the natural log of 1 plus alpha for alpha is an element between -1 and 1 inclusive. We can actually write this as its Taylor series, so its expansion is actually going to equal to n equals 1 to infinity of -1 to the n plus 1 multiplied by alpha raised to the n divided by n. So we're actually going to be replacing the natural log of 1 plus 1 divided by square root of t with its Taylor series. So we just let alpha equals 1 divided by square root of t. So when we do this, 1 plus 1 divided by square root of t, and this is actually this is such that it's less it's greater than 0, square root of t, which is also less than or equal to 1, such that t can be between 1 to infinity. Then its series can be rewritten as like so: infinity equals 1. And then I'm actually going to divide this by n over here. So this is -1 raised to n plus 1, and divided by n. Then replace with 1 square root of t being raised to the n. Then we can actually rewrite this. Infinity equals n, -1 n plus 1 divided by n. Then 1 raised to the n is just 1, no matter for whatever natural number you choose. Then the square root of t, so t to the 1/2, and then multiplied by n, that's t to the 1 n over 2, but it's a denominator, so we can write this as t raised to the -n divided by 2. Okay, so we can just replace this. We can actually replace the natural log of 1 plus 1 over the square root of divided by square root of t with this series here. And then by using properties of sums, I'm actually going to rewrite this. And I'm also going to define capital I to equal our our expression here. So I is equal to the limit as x approaches infinity. And I'm actually going to, since we're using properties of sum, I'm actually going to move the summation outside, and from infinity to n equals 1, -1 to n plus 1 divided by n. And then with brackets, I'm actually going to distribute the 1 over square root of x inside. So square root of x, the integral from 1 to x of t to the -n divided by 2 dt, like so. Okay, now now that we have that, I'm actually going to define the inside, the function inside to equal j of x. So I'm gonna let that be j of x. So then, you guessed it, we're actually gonna have to compute this integral here. So j of x is equal 1 over the square root of x, then multiplied by the integral from 1 to x of t to the -n divided by 2 dt. Okay. And now it's just computing the integral is just simple from here. So we're taking this in respect to t. So now we have that t -n over 2 plus 1, then divided by -n over 2 plus 1. That can be rewritten as t to the -n plus 2 divided by 2. Divided by same thing, and then I can just, since it's division, I just flip its reciprocal. So this is 2 divided by -n plus 2, t to the -n plus 2 divided by 2. Okay, and I'm gonna rearrange the terms. So this is simply 2 divided by 2 minus n of t to the negative n plus 2 divided by 2. And all this is being evaluated from 1 to x. Okay. Alright, that's nice. Now what I'm going to do now, before I actually do any of this evaluation, I'm actually going to rearrange. So what I mean is I'm actually going to factor out the 2 over 2 minus n outside, and then multiply the 1 over 1 divided by the square root of x. So it's going to look like this. Okay, so before we do this, well, we're going to do it anyway, but pay attention that when we plug 1, t is equal to 1, so it's 1 raised to any exponent, and for any choice of a natural number n, but it's always going to equal 1, so it's simply, when t is equal to 1, it's just 1 divided by the square root of x. So when we plug in for x, so this is simply just x raised to the negative n plus 2 divided by 2 all over the square root of x, but that also can be rewritten as so this is square root of x is equal to x raised to the 1/2, so it's the denominator, so this is minus 1/2, so this is negative n plus 2 minus 1, so it's negative n plus 1 divided by 2. Negative n plus 1 divided by 2. And then I can also rewrite it so it's 1 divided by x raised to the n minus 1 divided by 2. And then we can rewrite this as the square root of x, and then that being raised to the n minus 1. Note that 1 raised to the n minus 1 is like the same argument we're trying to state when we plug 1 for here. It's always going to equal 1 for, doesn't matter what exponent it is. And then this is just simply factoring out a 1/2, so this is 1/2 multiplied by n minus 1. So there it is. And now that we have that, so we have that j of x is actually equal to 2 divided by 2 minus n, and then multiplied by 1 divided by the square root of x raised to the n minus 1, then minus 1 divided by the square root of x. Okay, nice, fantastic. So now that we have this, we can actually substitute back for j of x, and I'm going to now I'm actually going to divide 2 to both sides when we substitute back for j of x. So this way we actually have capital I divided by 2 is equal to the summation of, or well, the limit as x approaches infinity of the limit from infinity, well, n is equal to 1 to infinity of negative 1 to the n, then divided by n times n minus 2. Let me stop here for 1 second, I'll explain what I did. So originally we have 2 minus n from here, so I actually rearranged the terms so it's negative n plus 2. Then I factor out a negative 1. But because there's a negative 1 in the numerator as the base, so originally we have with negative 1 raised to the n plus 1, so, and then we have a negative 1 on the denominator. So it's also rewritten as negative 1 raised to the n plus 1 minus 1, which the exponent is equal to n, like so. Okay? And then being multiplied by square root of 1 divided by the square root of x being raised to n minus 1, then minus 1 divided by square root of x. Like so. Alright? Excellent. So, now I want to define the summation right here to equal p. Okay? So really the next step is we're actually taking the limit as x approaches infinity of p. But before we do that, we want to evaluate this series first. So p is equal to the summation from n is equal to 1 to infinity of negative 1 to the n divided by n times n minus 2. And then I'm actually going to rewrite this so everything has the base x. So in other words, this can be rewritten as negative 1/2 multiplied by n minus 1, then minus x raised to the negative 1/2. Okay. Now, before we do the expansion, note that when we use our index for n is equal to 2, it's actually undefined. So this actually will later on we'll have to use L'Hopital's rule since we'll be getting an indefinite form. So what we want to do first before we do any of the expansions, we want to find the limit as n approaches 2 of this function here. Finding the limit at the critical point n is equal to 2. So find limit, yeah, there. I don't know why I wrote that. I don't know why I did that. Of critical point n equals 2. Then this is going to be the limit as n approaches 2 of now when I plug n is equal to 2 for the numerator, this is simply just 1, so we can just ignore that. So I can actually rewrite this as x negative 1/2 n minus 1 minus x to the negative 1/2 all divided by n times n minus 2. Then when you plug n is equal to 2, you get it if you get a 0 over 0. I don't know if I said infinity over infinity earlier. I don't remember, but it's supposed to be 0 over 0 in the indeterminate form. So that means we have to take L'Hopital's rule and then take the limit again as n approaches 2 after taking the derivative of the numerator and the denominator. Don't take the derivative as a whole as you're doing the quotient rule. That's not what L'Hopital's rule is. So use L'Hopital's rule. Then when we take the derivative, so this is the limit as n approaches 2. So be careful since we're taking this in respect of 2, so we're actually treating x as a constant. So be careful not to treat x as a function, as a variable. So this means when we take the derivative of the numerator, this is simply x raised to the negative 1/2 times n minus 1, then times the derivative of the exponent, which is negative 1/2. So this is negative 1/2, then multiply by x to the negative 1/2 n minus 1, then multiply by the natural log of x. Okay, and then the derivative of n times n minus 2, that's 2n, then n squared minus 2n, so that's just 2n minus 2. Okay, now when we plug n is equal to 2, so 2 minus 1 is 1, then this is x raised to the negative 1/2, so it's the 1 over the square root of x. So this is just in the numerator is the negative ln of x, then divided by 2 times 2, 4 minus 2, 2, then multiplied by 2 is 4. So there we go. So when n equals 2 for our index is equal to the negative natural log of x divided by 4 times the square root of x. Okay, so now that we have that, now let's actually expand the series out. So p is equal to, so when we plug our index n is equal to 1, so negative 1 raised to the 1, that's negative 1, then 1 times 1 minus 2 is negative 1, so that's just 1. Then over here is x to the 0, which is just 1, and then, okay, and then just 1 times 1 minus 1 divided by the square root of x. Okay. Then plus when n is equal to 2, well, we just showed that as n equals 2 for this series, or the this function in particular, so that means it's equal to minus ln of x divided by 4 times the square root of x. Okay. Now next is when n is equal to 3, so when you plug n is equal to 3, negative 1 raised to the 3 is negative 1. 3 times 3 minus 2, so that's 1 times 3, so that's a minus 3, okay? And then when you plug 3 here, this is 3 minus 1 is 2, So this is x to the negative 1, so this is 1 over x, then minus 1 over the square root of x. Okay, and then when we plug 4, so negative 1 raised to the 4 is 1, then 4 times 4 minus 2, that's 8, so plus 1 over 8. And when we plug 4, this is 4 minus 1 is 3, so negative 3 halves. So this is 1 divided by the square root of x cubed, and then minus 1 over the square root of x. Okay, and then it goes on. All right. So now that's it. Now that we have that, now let's actually take the limit as x approaches infinity. So the limit as x approaches infinity of p, plus p is equal to this expansion. So notice that when x approaches infinity, this is going to be 0, this is going to be 0, 0, 0, 0. So this piece, and from here all the way onwards, is going to equal 0. Note that when we plug infinity for this term here, we actually get an infinity over infinity indeterminate form. So we're actually going to have to take L'Hopital's rule for this. So this is simply 1 minus, and then I'm actually going to factor out the 1 over 4, and then write as the limit as x approaches infinity of ln of x divided by the square root of x. So that's what we have so far. Okay. Now let's actually focus on taking the limit of this function in particular. So again, you plug infinity, natural log of infinity over the square root of infinity is a infinity over infinity indeterminate form. So natural log of x, square root of x equals infinity over infinity. So we take L'Hopital's rule again. So this means we have the derivative of the top. So limit as x approaches infinity of 1 over x, then divided by the square root of x. Its derivative is 1 divided by 2 times the square root of x. Then I can also rewrite that as 1 times x, or 1 over x multiplied by 2 times the square root of x, by 1, so that's equal to 2 square root of x, okay. And then they have the same base, so I can actually rewrite this a little differently. So this is, and I'm actually going to factor out the 2, so it's 2 times the limit as x approaches infinity of square root of x is x to the 1/2, then minus 1, so it's 1 divided by the square root of x. So when you take x approaches infinity, this is actually just equal to 0. Okay, nice. So we have that the limit of p so far is equal to 1 minus 1 over 4, and that's multiplied by 0 as shown right here for ln of x divided by square root of x. And so that's actually equal to 1, but that's 1 is equal to I divided by 2. So this means I divided by 2, you just multiply by 2 to both sides, so you get that I is equal to 2. So therefore, we can conclude that, let me write this in purple, our conclusion. So our final conclusion is the limit as x approaches infinity of 1 divided by the square root of x multiplied by the integral from 1 to x of the natural log of 1 plus 1 divided by the square root of t dt is equal to 2, like so. And there we have it. That's pretty neat. That's actually a pretty awesome integral.